So vectors are useful in many areas of engineering. To help you deal with engineering simulations involving vectors, it is possible to define a special vector variable in ease. In general, a vector variable will consist of three scalar variables that correspond to the x, y, and z components of the vector. Many problems are two-dimensional, and in this case, you can define your vector as being a 2D vector so that the z component is automatically ignored by ease. To declare that an ease variable is a 3D vector, you must use the $vector directive, followed by a list of one or more vector variables. Each variable that is defined as a vector will have three scalar components that are designated with the subscript _x, _y, and _z. Vector variables can be assigned using the vector assign command, which takes three arguments corresponding to the x, y, and z components, as I'm doing here for a position vector. Note that every component of a vector has to have the same units, and I can assign the units in square brackets right here after the vector assign command. It's also possible to assign each of the components separately, as I'm doing here for another position vector b. Once defined and assigned, vector variables will show up in this upper region of the solutions window under the vectors category. Scalar variables will appear as usual, but here in the lower region under the scalars category. Vectors can also be assigned using the vector assign polar command, which requires three arguments. The first argument is the magnitude of the vector, and then the second and third argument are the angles between the vector and the x and y axes respectively, so theta x and theta y as shown in this figure. Note that because you are specifying the angle, you need to have the units for angles already set, and you would preferably do that using the $unit system directive as I'm doing here. Again, many problems are strictly two-dimensional, and therefore they are best dealt with using 2D vectors, which have only two components, so that the third component, the z component, will be ignored during any operations and computations. To declare that a vector is a 2D vector, use the $vector 2D directive, followed by a list of 2D vectors. 2D vectors can be assigned using the vector assign command, but in this case only two arguments are required, corresponding to the x and the y components. 2D vectors can also be assigned using the vector assign polar command, but again only two arguments are required, and these would correspond to the magnitude of the vector and the angle relative to the x-axis as shown in this figure here. There are a few vector functions that provide pre-assigned vectors which are often useful for calculations. So these include things like the zeros vector, as well as unit vectors in each of the coordinate directions, and these are all summarized in this table for both 3D and 2D vectors. You can access and manipulate each component of a vector in the same way as any other ease scalar variable, and it's possible then to carry out any vector operation manually. However, most useful vector operations can also be accomplished automatically, which greatly simplifies vector calculations. So for example, we can add two vectors v1 and v2 to get a resultant vector r by adding each of their components according to this formula. So here I can just manually add the components of v1 and v2 in each coordinate direction to get an r vector, which I've called rm. Ease allows you to accomplish vector addition automatically by simply adding vector variable v1 to vector variable v2 as I've done here. And obviously the result is the same, it's just much easier to do it this way. Subtraction or multiplication by a constant and so on can all also be done in this way. The magnitude of a vector is obtained according to this equation, and this operation can also be accomplished automatically. In this case you would use the vector mag function, which I have demonstrated here. The angles between a vector and the various coordinate axes are sometimes referred to as the direction angles, and they are shown in this figure. And these can be computed according to equations that look like this. So this one is for theta x, but you can imagine one for theta y and theta z. And these calculations can be accomplished automatically using the vector angle sub x function as demonstrated here. And of course, similar functions exist for the y direction, and if you have a 3D vector for the z direction. There are also utilities in ease for plotting 2D and 3D vectors, as well as taking their dot and cross products, We'll cover those in subsequent videos.